HLAA complex numbers and more, day number 2. Today we're going to focus on solving polynomial equations using long division and synthetic division to divide polynomials. Use the factor and remainder theorems as well as the fundamental theorem of algebra. Let's go ahead and get started. All right, let's go ahead and get started by visiting this idea of long division. Now, long division with polynomials is going to be used to expose the zeros or roots or linear factors of a polynomial. But in this case, we're going to keep it simple and just start with the basics of long division. So I'm going to take the number, let's go 13, and divide it into 2,495. So recall that we take this number, right, and we divide it into that said number underneath the division sign. So I find the first set of digits in which 13 goes into 2,495, which is 24. It goes into 24 once. So I multiply 1 times 13, and I subtract the result. I get an 11. I'm going to drop down, because 13 doesn't go into 11, I'm going to drop down the 9, making that 119. Now 13 goes into 119 9 times. So I'm going to put a 9 up here, and I'm going to multiply through 9 times 13. That gives me 117. Now I'm going to subtract that result, and I get 2. Now 13 doesn't go into 2, but 13 does go into 25. Goes into it once. I multiply 1 by 13, and I get 13. Subtracting the result, I get 12. Now 13 doesn't go into 12. I've got nothing else that I can bring down. Therefore, my result is that 2495 divided by 13 is equal to 191 and 12 thirteenths. Okay, let's apply that now to polynomial long division, and then we'll analyze what we have similar and different. Okay, so if I want to take f of x and divide it by g of x, I'm going to put g of x on the outside and f of x on the inside of my division symbol. Now, if you have any missing terms, write in a placeholder. So just put in like if I didn't have an x cubed term, I'd put in 0x cubed. But in this case, I have all terms descending down to my constant of -1. And we go from there. Okay, now what I'm going to do is I'm going to find out how many times x squared goes into 3x to the 4th. So 3x squared times x squared is 3x to the 4th. So I'm going to put a 3x squared appropriately above its like term 2x squared. Now I'm going to multiply through. So 3x squared times x squared is 3x to the 4th. 3x squared times x is 3x to the 3rd. 3x squared times -2 is a -6x squared. Now I'm going to subtract, just like I did over in my simple problem off to the right. I expect my x to the 4th terms to reduce out. That gives me x cubed plus 8x squared, and I'm going to drop down plus 3x. Since there's 3 terms in my expression outside division, I'm going to keep 3 terms consistent. Okay, now I take x squared and I multiply it by x to get x cubed. So I'll have plus x. Now I'm going to distribute x through all terms. So that'll be an x cubed plus an x squared minus a 2x. Again, subtraction. I'm trying to keep this as clean as possible. Okay, x cubed's terms reduce as expected. 8x squared minus x squared is 7x squared. 3x minus 2x is a 1x, and I drop down my -1. Okay, x squared goes into 7x squared 7 times. Multiplying through, I get 7x squared plus 7x and minus 14. Again, once more, subtract. And it looks like I get a -6x and a plus 13. Okay, we're going to analyze this in just a moment. So f of x divided by g of x is equal to 3x squared plus x plus 7, just like I had up here with the 191, plus my remainder over x squared plus x minus 2. Okay, it says find the quotient q of x and any remainder. So what is q of x? Q of x ends up being this. This is q of x. And r of x, we're going to put in red here, is our remainder function. And there you have it. That's how you do long division for polynomials. All right, so a theorem. For any two polynomials, f and g, there are two unique polynomials, q and r, such that f of x is equal to g of x times q of x plus r of x. Or f of x over g of x equals q of x plus r of x over g of x. I made a mistake here. I should have called this right here g of x. Okay, for all real values of x. The polynomial q of x is called the quotient and r of x is called the remainder. Notice that the degree of g is always going to be greater than the degree of r. Okay. If r of x equals 0, then g of x is called a factor, right? If I divided, for example, 20 into 1,000, 10,000, right? I would get 500 with a remainder of 0, right? So 20 is a factor of 10,000. Likewise, if I get a remainder of 0, f of x and g of x, excuse me, g of x would then be a factor of f of x. All right, let's continue and look at some more. All right, on this slide, we're going to use synthetic division to show that x plus 1 is a factor of f of x. Now, what I could do is I could use long division and take f of x and divide it by x plus 1, and I get some, q of x and r of x would equal 0. Right? It's saying show that. Right? It's a factor, thus that would be true. I'm not going to use long division here, but I'm going to use synthetic division. Now, the process of synthetic division is interesting and very closely related to long division with a couple of slight differences. We're going to add instead of subtract, and we're going to use a 0 or a solution. Right? We're going to say that x equals -1 would be, if x plus 1 is a factor, then x equals -1 would be a 0 of f of x. Therefore, f of -1 should equal 0. So let's go ahead and work synthetic division. How we set up synthetic division is we put that 0 right in a box. We put it right next to the coefficients of f of x. Okay, this is the basic setup. Now, since we know that we're trying to show that this is a factor of f of x, f of -1 equals 0, thus we are expecting for there to be a remainder. This is where r of x would show up. Okay, r of x to equal 0. So let's go ahead and execute the steps on synthetic division. How we do that is we drop the coefficient 2 down, and then we multiply -1 times a 2. So that gives me -2. Now, when we work with synthetic instead of long division, we add. So we're going to add these coefficients. So we're going to take the -2 and the -1 and add them. I get a -3. Now I take the -1 times the -3. That gives me a +3. Okay, so each subsequent value that I get here, I multiply by -1 to get the next sum number. All right, that number which will be summed to the next coefficient of the polynomial. Okay, so now I'm going to add -32 and +3. gives me a negative 29. Multiply negative 1 and negative 29, I get 29. Okay, I add those two together, I get a 60. And I multiply negative 1 times 60, I get a negative 60. And look at that, very nice. Okay. Now, what I can do is I could say that f of x is equal to x plus 1 times a cubic polynomial. Okay, now notice I have a cubic polynomial because I've divided a quartic polynomial by a linear factor. And that cubic polynomial ends up being the coefficients of what's left over right here. So that'll be 2x cubed minus 3x squared minus 29x plus 60. Okay, from there, I also ask you to write f of x as a product of linear factors and find its roots. That's not necessarily something that we're going to be able to do yet. We don't have that skill set yet. So what I'm going to do is I'm going to actually leave it like that. Okay, I'm going to leave it like that and just show you this process of synthetic division. We've got a couple of theorems coming with later that will allow us to go further with that. All right, let's continue to another example. Okay, you might recognize this. We actually used this in the previous slide. However, the polynomial remainder theorem is one that's useful, and you'll see it pop up on pretty often occasion. So given a polynomial f of x and a real number p, then the remainder when f of x is divided by x minus p is f of p. Right? We said on the previous problem when f of x was divided by x plus 1, it had no remainder, so it just equaled some function, right, with a remainder of 0. Then what that means is that if I solve this, set that equal to 0, then f evaluated at that number should equal 0. Right? That was the remainder theorem, just wasn't referred to as that at that point. Okay, so this example says when f of x is divided by x plus 2, the remainder is 3. What that tells me is that f of negative 2 is equal to positive 3. It says find the value of a. Okay, well, I know that f at negative 2 is equal to positive 3. Thus, I can say that 3 is equal to negative 2 cubed plus 3 times negative 2 squared minus a times negative 2 minus 5. And look at that. Now my only independent, or my only variable, is a. So I could do some algebra on that. That'll be a negative 8 and a positive 12 and a positive 2a and a minus 5. So I'm going to bring all constants over to the left side. That'll give me 2a is equal to 4 minus 1, that'll be positive 4. Thus, a is going to equal 2. So I've used the remainder theorem here in order to allow me to find the value for a, the coefficient of the linear term of that polynomial. All right, let's continue to the next slide. All right, the factor theorem. Very similarly and related to the remainder theorem. A polynomial f of x has a factor x minus p, where p is in the real numbers, if and only if f of p is equal to 0. So if f of p is equal to 0, if f of 5, let's say, is equal to 0, then x minus 5 is a factor of f of x. Okay, so using the factor theorem, show that x minus 3 is a factor, then use synthetic division to fully factorize h of x. And it should say, it looks like f of x here, so we'll call that an h of x. All right, so using the factor theorem, show that x minus 3 is a factor. Okay, so what I would do here is I would plug in a 3 and show that h of 3 equals 0. If h of 3 equals 0, then x minus 3 is a factor. So 2 times 3 cubed plus 3 squared minus 15 times 3 minus 18. If this equals 0, I know x minus 3 is a factor. Okay, so let's check it out. H of 3, use some algebra. That's, oh gosh, it's 27. That's 54 plus 9 minus 45 minus 18. Yeah, that's looking like it's going to equal 0. Okay, cool. So that tells me that x minus 3 is a factor. Now, I could go to two directions with this. I could use long division, or I could use synthetic division. I'm told to use synthetic division. I also want to use synthetic division. It's typically easier to work with, at least in my opinion. So here's a 3, right, for x minus 3. I'm going to use the coefficients 2 and 1, and negative 15, and a negative 18. All right, I'm going to go ahead and set this up. Drop the 2. I'm expecting a 0 here. Multiply 2 and 3, I get 6. That gives me a 7. Multiply 3 and 7, that gives me a 21. I add, that gives me a 6. Multiply 3 and 6, it gives me an 18, which of course adds to 0. Thus, I can say that x minus 3 times 2x squared plus 7x plus 6 is equal to h of x. Now, I want a fully factorized version of h of x. So I want to factorize this quadratic, 2x squared plus 7x plus 6. I'm going to put a 2x here and an x there. And I'm going to go with a plus 2 here and a plus 3 there. And that should, yep, that'll work out perfectly. And there is a fully factorized version of h of x. Now, it doesn't ask for this, but the zeros of h of x, the zeros, also called the roots of h of x, are as follows. X equals 3, x equals negative 3 halves, and x equals negative 2. You can get those from each of the linear factors right there. Okay, let's continue to the next example. All right, let's take a look at this next example here. I've got f of x is divisible by 2x minus 1. If I set 2x minus 1 equal to 0, then that means x equals 1/2. Thus, f of 1/2 is equal to 0. Okay, likewise, when divided by x minus 1, the remainder is negative 40. Therefore, when I set x minus 1 equal to 0, that means when x equals 1, f is negative 40. Okay, so what I'm going to do is I'm going to first of all plug in a 1. 1s are going to be easy to work with. 6 times 1 to the 5th is 6. 13 times 1 to the 4th is 13. 30 times 1 to the 3rd is 30. And 45, which of course will give me plus a plus b. And I know that when I plug in a 1, I'm going to get a negative 40 out. Okay, so let's simplify this, combining like terms. There's a 19. There's a negative 75. So 19 minus 75 plus a plus b is equal to negative 40. If I add 75, that'll make this a, what is this, a 35, and I'll subtract a 19. That'll be a plus b. Therefore, I'll get 16 equals a plus b. All right, if I plug in a half, I get 0. Okay, this is where a little bit of algebra comes in, obviously. So this will be f of 1/2 is equal to 6 times 1/2 to the 5th. Okay, so 1/2 to the 5th is 32. 1/2 to the 4th is 1/16. 1/2 to the 3rd is 1/8. 1/2 to the 2nd is 1/4 plus a over 2 plus b. All right, I know that equals 0. Okay. That's not allowing me to erase that. I'm just going to put a big 0 here. All right. So it looks like what I'm going to want to do is multiply everything by 32. Okay, so the left side will stay 0. If I multiply the first term by 32, I get 6. The second term by 32, I get 26. Third term by 32, I get negative 120. Fourth term by 32, I get, oh gosh, 45 times 8, which is 90 times 4, which would be 360. And then I get a times 16, 16a, and 32b. Okay, now let's combine some like terms here. 360 minus 120 is 240. 240 plus 32 is 272. Plus 16a plus 32b. Okay, over here I'm going to say that a equals 16 minus b. I'm going to plug that value in here. So this will be 272 plus 16 times 16 minus b plus 32b. Okay, expanding, that's 272 plus 256 minus 16b plus 32b. So 0 is equal to 528 plus 16b. Let's see what we get. So negative 528 equals 16b. B equals a negative 33. Okay, so B equals negative 33, and A equals 16 minus B. So it looks like I'm going to get a value of A equals 49. All right, there you have it. That is a way to use the factor theorem as well as the remainder theorem in order to determine coefficients for a polynomial. All right, let's get into the last couple of examples. All right, the fundamental theorem of algebra. If a polynomial f of x with real or complex coefficients has at least one zero or root, then there is at least one complex number, w, such that the output of f of w is 0. Basically saying exactly what we already knew about the factor theorem. Right? If we know there's at least one root, then there's at least one complex number which would satisfy that equation. The conjugate root theorem is also important for us to know. If a polynomial f of x has a complex 0, then its conjugate, z star, which we've talked about before, is also a root. So conjugate roots always come in pairs. Complex roots always come in conjugate pairs. So let's look at the example below. It says solve the equation finding all solutions on the complex plane. So this should not intimidate you. Right? All that this means is that there's going to be complex roots, right? Or complex solutions. So let's take a look at and solve this. Okay, so it gives us this. It says that z minus 1 minus 2i is a factor. Okay, so if I set that equal to 0, z minus 1 minus 2i is equal to 0, then z equals 1 plus 2i is a root. Okay, so that's one of the roots of this polynomial. Okay, now I'm going to bring it back over here and rewrite it in a separate form. Right? These are equivalent. I just didn't distribute the negative. All right, so this is a factor. Those two factors are exactly the same. And I just didn't distribute the negative. So using the complex conjugate root theorem, then we also know that z minus 1 minus 2i is also a root. Are factors of the polynomial. I'll just call it p of x. Okay? All right, therefore, what I can do now is I could multiply these two factors together. Right? So I'm going to take, and I'm going to say that P of, and actually this should be P of Z. P of Z is equal to Z minus 1 plus 2i times Z minus 1 minus 2i. Right? They come in conjugate pairs. As you can see, I've got conjugates here. Okay. And I'm going to then come up with values for A and B such that our polynomial would be true. Right? So take a look at this and analyze this real quick. Z times Z is Z squared. Times Z is Z cubed. Now I want that to be a 2Z cubed. Therefore I know A already. A has got to be 2. Okay, so I know that's got to be 2. I don't know what B is yet, but we're going to figure that out in just a moment. All right, so what I'm going to do here is I'm going to expand these first two linear terms. Okay, and I'm going to write P of Z along the way. All right, so if I expand those, Z times Z is Z squared. Then outside, Z times negative 1 minus 2i. So that'll be negative Z 1 minus 2i. Then I'll have a Z times negative 1 plus 2i minus Z times 1 plus 2i. I'm running out of space here. Maybe I'll make this a little bit bigger. There we go. And then last, I'm going to multiply negative times a negative, right? This negative. And I'll have plus 1 plus 2i, 1 minus 2i. All right. And then, of course, my other linear term, linear factor, if you will, 2z plus b. We'll figure out b here in just a moment. Okay. Let's continue with the green portion here. That's going to be z squared minus z plus 2iz minus z minus 2iz. And now I'm working on this. Remember, if we multiply conjugates, okay, z times z star, I got a quick little guy here. This is the same as the magnitude of z squared. All right, so the magnitude of this complex number, 1 and 2i, and of course, the modulus here is the square root of 5. So I'm going to square the square root of 5, right? So this is be square root of 5, squared, which will be 5. Okay, thus, that comes out to be positive 5. Okay, carry this along with 2z plus b. P of z equals that. Let's take a look on the inside here. Notice the iz terms. These disappear. 2iz, negative 2iz. See you later. Thus, P of z in factored form is going to be z squared minus 2z plus 5 times 2z. Now notice, let's go back up. Our constant term is a 5. Well, 5 times what gives me 5? That would just be a positive 1. Okay, now, it's interesting to note, this is a cubic. Okay, a cubic polynomial. Let's say it looks like this. A cubic polynomial, or an odd polynomial for that matter, has to have at least one real root. In this case, it only has 1, right? Could it have 3? Yes. But it can't have 3 if it has an imaginary root or a complex root. So notice that we have complex roots come in pairs. There's 2 imaginary or complex roots. Complex roots. And in this case, there's 1 real root. And notice that the number of roots add up to the degree of the polynomial. All right, have a great day, guys. We will see you in the next video.